Okay, so official lecture title, Artificial Intelligence and ChatGPT. So what we'll cover, artificial intelligence, what it is, some of its success stories. What do you guys know about AI? What have you heard, some things where it's done well, where it's outperformed humans? Yeah. So outperforming in the sense that it just does it faster than you, but not necessarily much better.
Yeah.
Okay. Yeah.
Well, it's better.
Yeah. I would go as far as say more like 30 years, but yeah, 25 anyway. Yeah. 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 There you go. I thought I saw a hand over on the side. Somebody? Yeah, so AI is a thing, right? What about things where AI is not so successful? What are some situations where humans are still outperforming the AIs? Yeah.
I would say I'm building
How so? What kind of building?
house.
Oh, you mean like designing houses? Obviously, physically?
Yeah.
Yeah, well, I mean, that's like a whole bunch of robotics built layered in on it, right? I don't know about the architecture world. Could AIs devise a house that's better? Maybe, right? But yeah, I don't know. Other stuff? Right? Like one of the things you see in the movies is always there are these giant, super powerful robots and they go off and do their things. And I'm always like, what powers those? They're always going to say, well, it's a fusion reactor. I said, well, fusion reactors could be pretty bulky. It's not just like batteries. Not much power does it make to, require to make the robot think, right? Because organic brains like ours, they're pretty good for certain kinds of tasks that come up a lot. Well, anyway, all right, cool. Well, that was good. Let's talk. So first we'll start off with computers. All right. So way back when, I want to see if my person is, if she's, oh, okay, 8 minutes. Wow. Why is it 8 minutes from UH? Okay. She'll be here when she gets here. So first electronic computers were just automated calculators, right? So if any of you have ever seen an abacus, you know what an abacus is? It's got, like a rack with some beads on, but basically not much different from that, but electronic instead of mechanical. And the first computers were used for pretty simple things like payroll and ballistics. Actually, the first large-scale usage of electronic computers was the U.S. Army in World War II developing artillery tables, right? So basically, if you have some enemy position over there and you have a gun with, such and such caliber and trajectory and firing a shell with so much weight and so much powder pushing it, where's that shell going to land? And so they made all these like calculations, trigonometric calculations. They could print them all up in the results in the books and give them to the officers. So that was one of the first things. Now, fundamentally, this has not changed. Even the idea of quantum computing fundamentally is not changing that. They're automated calculators. All computers are automated calculators with faster processors, more memory, and expanded instruction sets, right? And the fact that quantum is maybe around the corner still is not fundamentally changing that. For example, back in the day, when I was your age, uh, when I was your age, most of your age, unless you're old, the standard CPU instruction sets included options for subtraction and addition, but not multiplication. In the mid-90s, they started, having fairly standard ones being ones including multiplication. And, since then, they've come up with more and more bigger instruction sets, can do simple things faster, right? Multiplication is just basically a loop to do addition, but they made the CPUs able to do that. Okay. Now, AI is the field around making computer systems able to perform what are perceived as non-mathematical tasks, right? So remember, computers are just calculators. Math, in a sense, is their only thing they can do. So anytime a computer does a task, even if it seems like it's not mathematical, somehow it's been reduced to that. All right, so things like voice recognition, right? You look at the frequency and the intervals between sounds, and it figures out, oh, this is this person's voice because it sounds like you. Image classification, right? is this a face? Is this not a face, right? If there are a bunch of shapes milling around in an airport, how many people are there in the airport? And text sentiment analysis. So one of the things that big automated systems do is they have a large batch of text and they try to figure out if the overall tone of it is positive or negative. And they just look for words that they found to be associated with positive sentiment or with negative sentiment, right? And they just basically count those words up. It's not terribly sophisticated, but it may be good enough, right? It may be good enough and the process is fast. So humans, of course, can perform all of those tasks and largely without math, right? If you listen to two people, you can distinguish their different voices. If you look at two images, you can see which one has a face and which doesn't. And if you read an article, right, presumably you could figure out whether the author of the article thought well of whatever subject was or thought badly of the subject, right? And again, we do those without math because we're humans, we're not computers. So, but math is the only tool computers have. So all of this AI stuff takes a lot of math, mostly statistics, some calculus, and the goal is to approach and ideally even exceed human performance at tasks. Okay, that's what we're trying to do. Now, certain kinds of tasks naturally lend themselves to computers, right? It is not at all surprising that computers greatly outperform humans on things like long series of arithmetic computations, right? I can add numbers pretty fast for a human. You know, I can even multiply numbers pretty fast for a human, but obviously I'm nothing like, you know, even a pretty basic computer. Likewise, maintaining large data sets in memory, right? I know some stuff, but if you ask me to memorize a list of 1 billion names and somehow put them in a database and keep that in my head, realistically, that's not ever going to happen, right? But a computer's like, boop, yeah, no problem, we do that. Okay, but those aren't really, in the sense, intelligence, right? That's just basic, you know, stuff computers do. Likewise, certain things humans are far better at AI, at least right now, especially tasks that are not easily reduced to computations. So things like unstructured conversations, right? If any of you have ever tried to take packback off the rails, for example, right? You can start typing in some weird stuff into packback. And as long as you start off talking about IT or business issues, you can kind of put some weird stuff there in the text, and it kind of will say, yeah, okay, whatever, right? Back in the day, like I think actually in the 60s, some guy wrote a program to essentially function as a psychiatrist, right? Obviously, it wasn't, you know, a legitimate psychiatrist, but basically an interactive program that kind of felt like one. So you'd start a conversation with it. You'd say, hello, my name is Doug. And the program would say, hi, Doug, nice to meet you, right? Fairly tight script there. And then it might ask something like, how are you feeling today, Doug? And I would say something like, well, I'm okay. I'm a little bit old and I'm tired, and I'm probably more tired because I'm more old. And the program, you know, would latch onto those words like tired and old. It's like, oh, do you find yourself being tired lately? Or have you gotten older quickly? Or are you noticing your age? It would do stuff like, again, those kind of programs, you could pretty quickly take them off the rails, especially if you entered in really long slugs of text that it wasn't prepared to process well. And the same thing is true with AI today. Other things, image identification, right? So any CAPTCHAs where they try to ask, prove that you're a real human, right? And they show you the 9 panels. How many of these 9 panels contain traffic signs? Or which of these contain, you know, a bicycle? Things like that, they're not, computers aren't real good at, right? I can remember when they just showed straight up text and asked you to type it in, but then people started writing scripts that could recognize the text. So they had to do a variety of alterations where they show it hollow, you know, with just the outline, or at weird angles or overlapping, right? All kinds of weird tricks like that to make it tougher for the computers to recognize. But image identification is in many ways something that AI still struggles with. All right. Now, weak and strong AI, two different flavors, right? So weak is kind of where we're at now. Strong is where we'd like to be. Maybe it'll happen in your lifetime. If we get really surprising, maybe it'll happen in my lifetime. All right, so weak AI is where computer systems perform one task or a narrow set of pretty closely related tasks. For example, chess, right? And Go. Go is an Asian game that it's very popular over in China. It's actually substantially more complicated than chess. And so chess, the first victory against a world champion was in the late 90s. AlphaGo, again, took like 20 years later to actually achieve the same thing because the game itself is deeper. Self-driving cars, right? We were just out in California right before New Year's. Well, it was overlapping with New Year's actually. So we got out just before the fires hit. So self-driving cars, we saw it was the first time I'd seen them, and they were randoming around there where we were. We were in not Palm Springs, Santa Monica. Anyway, automated medical diagnosis, right? You teach a bot program how to evaluate symptoms, bring them all together, come up with a reasonable diagnosis. You probably do that about as well as a human can in many cases. Okay, so this is the current level. You write a program that basically analyzes factors and performs as well as, typical humans do. Well, strong AI is basically the idea that you have a big, powerful, multi-purpose brain system that could become proficient at pretty much any task, right? So currently this does not exist, and it's fair to ask, if this were actually developed, would it be cost effective, right? It would have to be, cheaper than feeding a bunch of ordinary humans. So this is a real question, whether that's going to happen anytime soon. I guess we'll see. Okay. Now, the idea of machines performing human tasks is actually really old. For thousands of years, humans have thought that, yeah, maybe machines can do some of this stuff. The earliest one I'm aware of is Talos from Greek mythology. The idea was around the island of Crete, there was this big bronze robot that he'd like fling like giant frisbees, rocks at boats coming in and wreck them. So he was kind of the guardian of the island. Later on, they had this was like in the 1800s, a machine called the Mechanical Turk, right? So I can pop up an image of that. Let's see if we get that good. All right. Okay. Now the Mechanical Turk, for all appearances, looked like this, right? Looked like it was. Imagine that those panels are sealed up, right? So it had it's not actually a guy, it's like a wood carving. And somehow mysteriously the pieces would move. So you would tell the human operator the move, and you'd move one piece, and then somehow the machine would mysteriously move another piece, into the proper place. And in fact, right, they had a little guy who was very good at chess stuffed under there. Somehow he like crammed in there and he was hidden behind panels. And that was the trick. So there you go. That's basically how they did that. But still, people were, it was like a big draw at circuses and other exhibitions, and people would pay to see it play. Anyway, so the early days of AI development, there were a whole bunch of debates around which problems to attack, what techniques to apply, and how to incorporate learning. And the idea was, this change from being myth to being fraud to being, hey, this is something that to some extent can be real, can be done, but we want to get some good successes early on, right? We want to get, if any of us are, the AI guys, if any of them were going to make a name for themselves in this field, it would be by having something successful, right? Not some fraud or failure. So probably the earliest, most publicized AI successes were defeating world champions in pure skill games. Actually, backgammon, computer defeated the world champion of backgammon in the 70s. And, backgammon is not a terribly complex game. And according to the writer of the program, he still thought that the human player was better. It's just that the computer got some lucky dice rolls and managed to win. There are other games, for you guys know Connect 4, right? Yeah. Somebody did a mathematical proof in the 70s showing that the player that moves first in Connect 4 has a guaranteed win if they don't screw it up. And so stuff like that in the 70s, that wasn't really AI, but, it was a step along the way. But the first real big one was in chess in 1997, right? They had, I think it was IBM's Deep Blue against Garry Kasparov. Gary was the world champion from like the mid 80s for quite some time afterward. There was a big publicized match with him around 1990 where he won, but the computers kept getting stronger. So I'll talk about this with chess because chess is something I know a little bit about. Back in the day, I was pretty good and for a human, and currently the faculty advisor to UIC's chess club, so that's something. Anyway, so in chess, you can distinguish between two kinds of situations. Number one, tactics. So tactics are short-term concerns. Typically, that's to grab some short-term typically gain some material advantage, like win a pawn, win a piece, something like that. Strategy is longer-term positional play. You don't see exactly how it's going to play out at the end because you can't see that far ahead, but you recognize that you're in a situation with some good factors that if you don't screw it up, you'll be better off later on. Okay, now, early chess programs had excellent tactics, but a lot of strategic deficiencies. All right, so I'm actually gonna pop in and dig out one of my games here. I have a few of these that I keep around, just to give you an idea of what's going on. So let me check my library. Home, library, more. There we go, library. Okay, so I'll dig one out. Is that a good? August 26th. I don't play that much. Let's see. Oh, against Wallybot. Maybe this is a good one. Let's see how it goes. All right. I want to blow it up. Okay, yeah. Okay, I'm going to pause it for a second. Okay. So right now, all right, we've just been kind of moving stuff around. I feel pretty good about this. I have a little bit more space than the other guy. And the computer analysis, if I fired it up, they would say, yeah, you're doing pretty good, right? But if you're just a casual player, there's nothing here that says, obviously, wow, you're just going to crush this guy, right? So at this point, I'm starting to feel kind of good about my position. I'm gearing up for an attack over there. His knights are over on that side away from the action. Let's see what happens. All right, so let's play a little further. All right. Now here, things are getting a little bit closer for me, right? So what I'm going to do next is I'm going to try to move that pawn to open up that line, bring my rook into the game, and he doesn't have much he can do in terms of defense, right? His knight's kind of out of the game. So I'm starting to feel better about this. Again, nowhere near seeing this through to the end, right? But positionally, strategically, I'm starting to feel like, yeah, okay, this is not bad for me. So we exchange a few pieces. Okay. Now things are starting to see, or I'm starting to get more concrete threats here, right? I'm starting to have threats like, hey, I could push that pawn and maybe take that pawn with the bishop, fork the king and queen. I'm dominating that file. Even if he exchanges, I can bring my rook over. His king's in the way of the other pieces. Again, not to where I can see this through to the end, but I'm starting to feel quite good about the position at this point. Okay, and now is where things start to get weird, right? So you'll notice I have two bishops and a knight. He has a bishop and two knights, so that's about even. We both have both our rooks, both have our queen. That's about even. He's got 4 pawns, I've got 3. So I'm actually starting to give up some material because I can see his king is going to be so exposed, it's just going to be bad for him. Okay, for the record, these are all pretty decent moves being played on both sides from here. Okay, but what I'm doing at this point, I've sacrificed 3 pawns, right? I've sacrificed 3 pawns. He's got 4, I've got 1, but his king is in such a bad exposed spot and he doesn't have anything to defend it with that I'm just gonna start to wreck him now. All right, this is where things start to really go downhill. So tactically now, with that, I'm sacrificing a rook, right? He can take it, but if he takes it, it's going to be disastrous for him, but he has to take it pretty much. But he doesn't, he wanders away, so I get his queen. All right, and now, for those of you who play chess, you know, all of that, you know, from about 5 moves ago, I could see that out to the end, right? Because this is just tactics at this point. I've got a queen and a bishop against his rook. You know, he's pretty much toast. It's just a matter of grinding it down. So the same thing happens when computers are playing chess. It's just they see stuff a lot earlier than I do, right? So if we take Magnus Carlsen, you guys know about Magnus Carlsen, right? Yeah. If we take him as a baseline, this is Magnus. This is me. I'm down here, right? Maybe if I played him 1,000 games, maybe I get one where I manage to hold him off and draw it. Maybe. He's that much better than me, no question, right? The best computers in the world are that much better than Mr. Carlson, right? He does not have that much of a chance against any of them. So that's kind of where things are. But the analysis they use on these, they can see all of the same things I do, just like 10 moves sooner. They can recognize these factors a lot better. All right, but it's the same principle. Okay, so now early chess AI was pretty much a brute force algorithm, right? We talked about brute force algorithms in security. They basically analyze every possibility. So the early chess algorithms, they said, well, let's try to analyze every possibility like a few moves deep, right? Or however many moves we can. But the number of moves branches out very fast, right? So if there are 20 possibilities for white, then there's 20 possible responses by black for each of those, and 20 responses to each of those for white again. So basically, the number of moves ahead you're going to look is something like 20 or 30 to whatever power. So it gets very big, very fast. Now, it is true that computers got faster and were able to consider more moves, right? But typical positions requiring had many possible options, had to look many moves deep to get a good decision relative, for what a really good player would do. And so it was a problem. Computers just they were getting faster, but they weren't getting that much faster to where they were making much headway just by brute force. So in order to look deeper, you had to try to prune the trees, right? So the tree is the set of all possible moves. If you see it branching off in all its different ways, you'd look at the really bad moves and say, wow, that's a bonehead move. No point even considering past that, right? So in some sense, brute force methods, yes, if you had infinite time and computing resources, they'd give you the right answer, but nobody has that. So basically what happened with these kind of brute force algorithms, they got good enough to defeat most human players. If you're a casual player, yeah, that kind of brute force algorithm is going to grind you down because you're not that good. All right. Even against me, they'd have a decent chance. But if they're playing against top players, no, those guys really understand the game far deeper than this kind of analysis would provide. So the alternative was what are called heuristics. So heuristics is kind of a fancy word for rules of thumb, right? It's a guiding principle about how to do something. So brute force models did evaluate positions by material and positional factors, right? They'd say like, oh, you're ahead of rook and that's real good, or you have an advanced pawn, or your king is safe because you've canceled. They did factor in all those things, but heuristic models relied a lot more, right? So if some path of move seemed obviously bad, they drop that pretty quickly. But problem is with heuristics, they're never universal, right? Every chess position is a special case, right? So for example, if you have a pawn on the 6th rank, that's going to be close to getting promoted. If you get a pawn all the way across the board, you can turn it into another piece like a queen or something. And in most cases, many cases anyway, advancing it from the 6th to the 7th rank, so it's one move away from promoting, is usually a really good thing to do, right? But not always. Sometimes advancing the pawn could make it vulnerable and lose you the game that you might otherwise win. All right. So if you try to implement that as a heuristic, you say, oh gosh, I have a pawn on the 6th rank. Pushing it is going to be a huge thing. I should mostly do that. Sometimes it's right and sometimes it isn't. And if you're playing against somebody that really knows what they're doing, right, it's going to be pretty dangerous. So kind of what they're doing with that is more advanced heuristics, right? Not just brute force and not just heuristics, but the idea of trying to understand the context where the heuristic is applied. Okay, so neural networks are essentially statistical models designed to detect small influences or interactions between variables, right? So, for example, suppose you call the event of advancing a pawn from the 6th rank A. Okay, so A is moving that pawn from the 6th to the 7th rank. If there are some factors that will call B, then moving that pawn wins. If there are some factors that will call C, moving that pawn loses. And ideally, neural networks would identify both B and C. They would try to say, well, is this position a good one to move that pawn or a bad one to move that pawn, right? And neural networks are just kind of advanced statistics that look at all those factors. They say, we know that sometimes moving the pawn is good, sometimes not. Let's figure it out. Okay. And I realize now I should have done a question, so I'm going to do a question. Let's do one. And we'll come back to this. Okay. We'll do an easy one. Ooh. All right, we'll do 28. 28's a good one. I'll do one more in just a minute. I'll do two because we're a little bit backlogged. All right. 28's going to be question number one. I'll do another one in a minute. I'm going to try to get these done quick because I'm going to end them both at a minute. So plan accordingly. All righty. About 10 seconds. Get those answers in. Okay. Oh, just under the rug. Okay. Under the, wow, look at all that. Okay. Fine. Let's do one more. Correct answer, elastic means allow quick changes in resource usage. Yeah, good. See? All right. Ooh, we'll do 23. All right, cloud service models. Let's see. Let's see who remembers cloud service models. All right, winding down, just a few seconds, get those answers in. Oh, jumped up to 81 there, look at that. Okay, ooh, 82. All righty, correct answer is, which one has the most software? This one, right? Software as a service comes with all the programs ready to use, has more than platform as a service. Platform as a service at a minimum has an operating system, might also have some plain vanilla applications of whatever the cloud service specializes in. Infrastructure as a service is just bare metal machines. You got to install everything yourself. All right. Yeah, that one was tougher. All right. Not bad, though. Not bad. Okay. And so, expert systems. So one of the applications of AI, besides just, getting good at games, was training machines to make decisions about as well as human experts, right? For example, you might design an expert system for medical diagnosis based on following rules, right? If patient exhibits symptoms A, B, and C, prescribe treatment, whatever. But expert systems rarely lived up to their hype. In fact, 20 some years ago, not much more than 20 years ago, when I was an undergrad taking IDS 100, which was the earlier incarnation of IDS 200, one of the things we talked about in there was basically different kinds of, primitive AI. So they had what were called decision support systems and expert systems. And I remember asking the professor, how come, our expert systems a big thing? Are they going to be taken over? And he's like, no, probably not. It's kind of a dead end in the evolution of this kind of thing. And, clearly what's taken over is machine learning. I think very likely we're going to see some kind of little bit more of a hybrid of these things. Again, just like with chess, we saw a hybrid of brute force and heuristics. You have to look a certain amount in depth, and you have to apply heuristics, and you have to apply heuristics to heuristics. And presumably, you could add in layers of heuristics around when to use certain heuristics about other heuristics. Same kind of thing with expert systems. There's a lot of different factors going on that just saying, oh, if a patient shows symptoms A, B, and C, prescribe this. It doesn't work too well for complex systems. So, real reason why expert systems didn't live up to their hype. Number one, real world systems are much more complex than chess, right? Chess seems complex when you're playing it, but it's a pretty finite game, right? Pretty finite and artificial. Number two, available data is much more limited. If you're trying to train a chess game, what they do is they have those two applications face off against each other and play billions of games and thereby figure out what works and what doesn't. They get enough data to make reasonably good decisions. But you can't feasibly do that in terms of medical applications, right? You can't just round up a billion humans and try a variety of treatments on them and see what works. And, especially since they're not going to all have the same problems. And of course, outcomes may not be observed for a long time, right? You can get two applications on fast machines playing that billion games very, very quickly. It will take you a long time to even round up that same number of humans. And if you provide the treatment, it's going to be a long time till you see the results and until you see any side effects. And finally, new cases can be dissimilar from older ones, right? If you're playing chess, chess is chess, right? It always starts from the same position, operates with the same rules. So the only difference is the moves that you make. But humans, all sorts of different factors happen, right? So for example, suppose you tried to test out some new drug as a treatment for cancer, right? Obviously, most people that get cancer are not particularly young, right? They're, my age and older, most of them. And so you develop a treatment based on that pool of patients. But what happens? Well, if you start branching outside of that, then, your treatment might not be as effective as it could. Or you might be limited in some sense. For example, suppose the pool of patients you have is largely from one particular ethnicity, one particular part of the world, right? One particular set of living habits, right? Americans, are rather uniquely suffer from diseases of affluence, right? The fact that we don't have to move around physically too much, that creates a lot of health issues for us. Other things, richer countries tended to be the first ones to smoke a lot and experience bad consequences from that. So if you do new treatments, if you try to apply the existing treatment to new populations that are different in some way, you might not get the same results. All right, so this is why expert systems, they started off looking pretty good. They were trying them out in things like auto shops, and pretty much one car of a particular make and model is going to be pretty similar to, another one. There's going to be differences in wear and tear and how the owner handles it and where it's been driven, but pretty similar. But there's a lot of variety in humans, and that's kind of where the problems happened. All right, so where this all led to is something called machine learning. So the idea of machine learning is that computers could learn without actually being programmed to solve a particular problem, right? So in the context of chess, you would explain somehow to the computer what the rules of the game were and just let it practice a whole bunch of times to see what worked and what didn't. Okay, so around 2010, you started to see that a bunch of factors coming together, right? The big capabilities of computer hardware brought together in massive networks, combined with the availability of very large data sets, started enabling machine learning. Typical example of that, like Facebook, right? Facebook has a pretty good idea at any moment what you're going to respond to in your feed and what doesn't, what you won't, right? They're not 100%, of course, but it's way better than random chance, right? Out of all the people that could post something on the variety of topics they could post about, Facebook has pretty good calculations in place about what you're going to respond to. And the reason is they have very large data sets, right? They can look back and say, hey, under these kind of circumstances, you commented on this particular post from this source, so we figure the chances are good that you're going to do it again. And they're widely used in a variety of contexts besides just Facebook, things like Google search results, things like YouTube video recommendations, right? They can basically figure out what you responded to in the past and reasonably assume that you'll respond like that in the future. And if you don't, well, that's just one more way that the system can keep learning, right? Because obviously people's preferences change over time. There are people on Facebook that you maybe interacted with a lot, and then you have a falling out, and then you don't. Or there's a topic you're interested in searching for Google for a while, and then you stop being interested. Or you're watching particular YouTube videos for a while, and then you're like, okay, enough of that. I'm going to go watch something else, right? And the system eventually picks up on that. Now, the way machine learning works, right, is pretty similar to neural networks from chess a few slides back. So again, different chess situations have different outcomes. In this case, you can just generically treat factors leading to wins as being good and factors leading to losses as being bad. And so in order to win, you would tend to pick moves that achieve good factors, right? So just like I did when I was showing that chess game up there, I was like, all of those different situations, they're stepping stones to victory, right? You can recognize early on that, oh, I have these little factors that seem good. Those factors, I follow them. I lead to new situations where the better factors become bigger and more clear, and I recognize them. And eventually it gets to the point where even a human player can tactically see their way through to the end, and they know that they're in good shape. Okay. So, and that's essentially the same thing as the computers do. Now, this, of course, is a lot more commercially valuable outside of things like chess, right? Chess is not a huge market, but Facebook feeds, there's a lot of money there. So factors leading to greater engagement, right? If Facebook shows you some content and you seem to interact with it positively, then they're going to classify that as good. And in order to improve engagement, arrange each user's feed in accordance with those factors, right? Basically, you come up with a neural network, this advanced statistical model that says, hey, these are all the factors that we see in posts that you positively interact with. We're going to show you posts that are similar in that sense. Okay. Now, again, this is IDS 200, so we're not going to do any of the math for machine learning. If you decide to be an IDS major, we have advanced courses, you can do some of that. If you decide to get an IDS minor, same, advanced courses, you can do some, right? If you really want to, you want to take it as an elective, well, there'll probably be room for you. Okay, but we're not going to do any of the math here. However, even though we're not going to do any of the math, it's worth mentioning the data sets involved are generally huge, right? So you wouldn't do any of the math anyway. You would push a button to tell the computer to do the math. So the machines do the computations. The role of the humans is, number one, to build the models, right? To get, for example, we talked in regression modeling that some variables could be more important than others in predicting an outcome. Well, as a human, you get to potentially decide, what is the threshold for significance, right? How impactful does a variable need to be before you include it in your model? You also get to interpret the results. Now, with machine learning in particular, it's pretty difficult to do that. Neural networks are kind of a black box. You push the data in and the system tells you the results. But because it's so complicated, right? Because you have factors interacting with other factors, possibly interacting with other factors, it's really hard for the machines to explain to humans exactly what's going on, right? But I'll give you an example. This is the same thing I do later on when I talk about YouTube, right? So basically, machine learning is about picking up very small but statistically significant patterns in data. Okay, so for example, suppose there is a 4-part video of some, what's a movie? What did we see lately? I don't know. Of some movie, say Inside Out 2. Okay, we took the kids to see that. So maybe there's some 4-part copy of that on YouTube. Okay, and it happens that most people who view part 1 go on to view part 2 and so on, right? So even though this is a pretty small batch of people, right? And let's say, finally, let's say Inside Out 2 was not terribly well known and only a few thousand people viewed it. Okay, so what we would see is basically just like we were talking about in our data analysis when we talked about support and confidence and lift. This is that same kind of thing, right? It's just the math is a little bit different. The determination is a little bit different. But we would say for this small group of people, viewers, we notice a clear pattern, right? In regression analysis, if you look at the entire pool of YouTube viewers, this thing wouldn't even be a ripple. You would say, yeah, there's a few thousand people out of the billions of people watching YouTube. This is not a big significant pattern. We don't care. But if you drill down and say, hey, out of this small pool of people that they saw part 1, they go on to see part 2, and the people who see part 2 go on to part 3, we're pretty sure that if we show up part 3 for them in the recommendation, or part 4, the people who watch parts 1, 2, and 3 are extremely likely to keep watching through part 4. So, excuse me. So machine learning is really good at picking up small patterns like that, patterns that are too small and isolated for regression to really pick up, right? Regression is great at figuring out the big trends in an entire batch of data, but there's a lot more detail there that regression analysis misses out on. But one of the downsides is it's real easy to explain regression analysis, right? You can say, hey, yeah, hot dog sales. If the weather's hot dog sales go up. If attendance is high, hot dog sales go up. Machine learning would look and say, well, you know what? If it's raining and it's on a weekend and the game is in the afternoon and they're playing another team who's high in the standings, then we sell more. But under these other batches of circumstances, not so much, right? So machine learning often gives much better predictions than basic regression analysis, but it's harder to explain to humans too. And that can be an important consideration in the business world when you're trying to explain to your boss or the CEO why you're doing what you're doing. All right. Anyway, so these are the things that humans do, right? They build the models, they interpret them, they adjust them, and they think about new data sources to bring in, right? That's basically the role of the humans, and the machines do all the number crunching. Okay. And again, you can think of all sorts of basic defects if you just treat data as identical, right? As every point as being equally important. So, for example, if you're Facebook, you're arranging the feed to try to get more money off of it somehow, right? Ultimately, you want to show more ads that you hope people click on. Now, to a certain extent, even if somebody's on Facebook and never clicks on any ads, they might be very nice and useful to have on Facebook more because their posts might be interesting to other users, and those posts keep those users on who are clicking on ads, right? But all else equal, you would figure that making a user who clicks on ads happy is more important than making one happy if they never click on ads. Other questions, older data versus more recent data, right? What's the relative importance? This is always one of those things in data. If you go back further in time, you have a bigger pool of data, you'll have less sample size errors, right? Less sampling error, but some of your data will also be less relevant. There's always kind of a trade-off. And the way that you figure out what works better, again, back to here, you can try different boundaries on what data to include in your model and see which one gives better predictive results, right? Which one is better at predicting whatever you're looking for. Okay. Now, all the assumptions built into modeling naturally lead to different AI processes, right? So chess has strict rules, and the outcome of the game is either going to be a win or a loss or a draw, right? It's very black and white that way. Other problems, there are no rules and no guarantees about what the model might find. Demands a different technique, right? So, for example, suppose you have a batch of possible ads to show to a customer. Which one of those is most likely to entice that customer to buy? Well, you know for sure one of those ads is going to be the best, right? Or you might have a small set that are about equally good, but one of them is going to be the best. And you know that you only have a finite set of ads. So that's kind of more like the chess problem. Or you might say, what are attributes of the customers likely to buy product Z if they've already bought product Y, right? So you have some pool of customers, right, which we'll call ones that have bought Y, and you want to show them Z or some other product. Well, you don't know exactly what factors are going to be important, right? It could be a few, it could be one. It could be that you don't even have the data currently to do a good job of explaining and predicting that. You might need to get more data. So this kind of problem is more like that. Don't know exactly how it's going to play out. So there are three families, three general approaches to machine learning. The first one is supervised learning. Supervised learning is for cases where outcomes are known, and the problem is just to find which factors lead to them, right? So for example, in chess, does this move contribute to a win or to a loss? If you're looking at security tools, right? Is this particular event likely to be associated with a threat or probably harmless? If there's an image known to contain a face, can you find the face in the image? Okay, these are things. Now, image classification. Let's see if this how that works. There we go. All right. So this was from a movie a few years back. Can you hear it? Let's find out. I got to crank it. Okay, 1 second. Okay. Oh, maybe you can't hear. All right, there we go.
That a dog or dog, pig, dog, pig, dog, pig, pig, loaf of bread, system error.
Right. So, but that's kind of what can happen. Basically, image classification is really difficult. It's something that machines struggle with, right? And the movie, well, it is what it is. But a very real simple problem, if you have some background like this, I'm going to draw a box and I'm going to fill it in. Okay. We'll draw another circle. Fill it in. And we're going to draw a couple more circles. Okay. As always, look out Disney. Okay. Everybody recognizes this is a face, right? It's not a particularly well-drawn face, but you look at, yeah, there's the face, right? And machines don't have problems with this either. What machines have a problem with is this. You do some kind of simple bar down the middle of this face, and suddenly the machines have a lot of trouble filling in those gaps, right? As humans, we're designed to be able to kind of blur those sides of the face together, right? We kind of see, oh yeah, that's a human hiding behind a red stick. We see that, right? But the machines, they're looking in detail. They're like, well, you know what? A face has some roundishness overall, and it has two roundish eyes and maybe like a half circle for a mouth, maybe a nose, maybe not, whatever, right? But this, hey, this side of the face isn't round. This side of the face isn't round. You have to like specially code it to be able to ignore that red line in the middle. All right, so it's a problem. Okay. Anyway, excuse me. So it's pretty easy to estimate the model accuracy if the outcomes are definitively known, right? If you have images containing a face or a certain number of faces, how many does the AI find, right? How often does your chess app win? How often does it lose? All right. Unsupervised learning, though, that's used when outcomes are not known, and maybe you can get some new and surprising and useful insights, right? For example, defining market segments, right? What groups of customers buy the same kinds of products? Well, you don't know how many different segments they're going to be, right? You have some massive pool of customers. Maybe there are two main categories of customers. Maybe there are dozens. Maybe there are hundreds that you can usefully differentiate between. Okay, significant association rules, right? People who watch video A might like another video B. if you're an operation the scale of YouTube with like 1 billion videos posted, you don't know exactly what outcomes you're going to find there, right? You're pretty sure that there are going to be some. There are going to be pockets of viewers that are more likely to view certain sequences of videos, but you don't know who they all are and how likely they're going to be. And finally, find a face in an image if there is one, right? You might be doing some automated security monitoring and you're looking, hey, do we find faces in this image, right? And over, you're looking at different frames of video footage and trying to capture that face, right? You're trying to see, oh, is this a person? But you don't know in any particular frame if there is a face. All right, so in this case, model accuracy is relative, not absolute, right? This kind of situation, supervised learning, you know exactly how good your model is, right? This one, not so much, right? What's the relative accuracy of saying you have 50 groups of customers versus having 51 groups of customers? You have to kind of wait and see and sell a bunch of stuff. And yeah, maybe you can do A/B testing with that to a point, but even if you test 49 and 50 and 51, you're not going to be completely sure that maybe 48 wasn't better or 52 wasn't better or whatever. Okay, so again, here you can compare models against each other, but it's always kind of open-ended that it might not be that way in the future. Okay, finally, reinforcement learning. This is the last bit. So reinforcement learning is actually very different from those first two because it's multi-stage, right? Supervised learning, you have an example, you figure out a solution. Unsupervised learning, you have an example, you figure out a solution. You're not quite as sure how good the solution is, but it's still a single stage problem. But reinforcement learning basically talks about how different agents interact with each other repeatedly, like in a chess game, right? So, for example, if your basic problem is to identify good and bad moves, right? What happens in chess is some badnesses are not immediately observable, right? So one of the things, anytime you move a pawn forward, you might be strengthening your position. It might overall be beneficial, but you're also creating positional weaknesses behind that pawn because since pawns only move forward, anytime you move a pawn forward, it means there are certain squares that pawn will never be able to attack ever again, right? So there's always that kind of trade-off. And there are things like that in a lot of places. Medical treatments, for example, right? You treat somebody for one thing, but long-term, it might create some problems. And it's going to be a while before you see how significant those problems are. So every action potentially has pros and cons. In machine learning, those are called rewards and regrets. And some rewards and regrets may only manifest after multiple interactions within a system, right? So again, if you're looking at this as far as chess, you might say, well, okay, I'm going to make this move. Immediately, I see what I think the rewards are. The regrets, well, it kind of depends on what the other guy does. He has to, he has to punish me for my foolish mistake. So this kind of reinforcement learning, basic research questions are, number one, how to learn efficiently as opposed to brute force, right? So think if you're making some massive machine learning model, some massive AI model, Gen AI, and you're trying to gather like untold terabytes of data from the internet that you can use to respond properly to individual questions, right? So the first thing is you don't want to rely. So early on, you always have to rely on human responses, right? The AI will toss you out some response to whatever you're doing, and you need human operators to say, this is a good response that makes sense, or this is a bad response that doesn't make sense, right? Or maybe to grade them, to say that, well, some of these responses are pretty good to very good, others are kind of bad to terrible, right? You need that kind of human interaction because the machines aren't really going to know. The machines by themselves don't understand grammar and logic and the reality of the world. So you have to learn efficiently because those human hours are really expensive, right? Machine hours are cheap, but the humans, you're paying them like $10, $15, $30 an hour to do this work. And the second question is, when is the model good enough, right? If you're talking something like supervised learning, something with chess, you can have the machines play against each other like 1 billion times. And if you have it play against each other 10 billion more times, and the numbers aren't really budging at that point, you're like, well, this is probably about as good as it's going to get until we have some massive genius breakthrough that gets us to the next level, right? But something like, how good the quality of text recommendations are, right? You ask it to generate an email on some topic or generate some ad copy, how do you know when that's good enough? Well, it has to have this kind of iterative process. And it's really a lot harder to get. So this is one of the things that differentiates the so-so AIs from the ones that are going to move forward. Just like, we'll talk about it with Google eventually, Google versus Bing. So right now, Bing, as far as the quality of its search results, it's kind of a lot how Google was maybe 20 years ago, right? It's decent, but it's not good. It's not that smart. It doesn't really include a lot of detailed factors. And I think you're going to see all your different AI platforms kind of branch off in that way. It's quite possible that the same thing that happened with search engines is very much going to happen with this sort of artificial intelligence, where there's maybe only one or just a few big players, because those are the ones that have, the real scope of data and analysis expertise, that they've come up with really good answers. And the fact that they come up with really good answers, just like Google, means they keep on bringing in new revenue to keep constantly improving their model, right? I guess we'll see. There's, all this has a long way to play out, but if you were going to ask me, knowing what I've seen in the last 30 years, that would be my guess. So anyway, we do have a few more slides on ChatGPT, but I'm going to leave these and we'll talk about these first thing on Thursday, right? And then I'm going to kind of just basically have a discussion session then. So I'll do one more iClick. Oh, by the way, for people that have been seeing my weird ass screen background all semester and wondering what's up with that, this is AI generated. So I went to Microsoft's thing and I said, hey, give me some images of kiwi birds performing a dark ritual. And this was the creepiest one I got. So I decided to keep it and use it as my screen. So AI. All right. Anyway, let me bring up the last iClicker question and then I'll have that. Okay. All right. We'll do 20. Service-oriented architecture and go. Yeah. You again, Troubles? All right, you can email me. Yep. Yeah, just go ahead. I know who you are. Yep. All right. I guess I'll wind this down in a bit. What's happening?
Lecture last Thursday, and I emailed you, I'm not sure of my documents. I just want.
That's one of those things that would be covered by, I mean, everybody gets a few no questions asked absences, so that'd be that. But as long as you're here most of the time, you'll be fine. Yep. All righty. I guess we're winding down. So if anybody has any responses, get them in within the next pretty soon. Winding down here. Oh yeah. In case anybody was wondering, service-oriented architecture is combining small modular applications. So D, if you got D, hey, not bad, 51%. Okay. We'll see you all next time.